Hello, my name is Joaquin Mayorga. I'm a postdoctoral scholar at the Evans School of Public Policy and Governance at the University of Washington in Seattle. I'm happy to record this video for the upcoming 2024 Data for Policy Conference. I will present an ongoing project about understanding discrepancies between self-reported and measured climate shocks in small-scale agriculture. This research is co-authored with my Evans School of Public Policy colleagues Didier, Alia, Andrew Thoms, Rebecca Toole, Stanley Wood, and Leigh Anderson. So let's get started. In this project, we examine patterns in self-reported climate shocks, how self-reported shocks compare to the measured record, and provide insights into risk perceptions and ultimately adaptive behaviors. The presentation is structured as follows. First, we motivate our analysis by asking why does any mismatch between self-reported and measured climate exposure matter? Second, we review theoretical contributions from economics, psychology, and social psychology. Third, we describe our empirical approach using household surveys and climate records for Ethiopia and Malawi. And in the last section, we show preliminary findings and conclude. We are using the IPCC's conception of risk, which is the probability of a negative event occurring, conditioned on exposure, that is how wide and how long it is, and vulnerability to that exposure. Drought and flooding have affected Ethiopia and Malawi in recent years, affecting livelihoods, as we will see in the news clips in this slide. As we look into the household survey data, we see that a substantial number of people in rural agricultural households report climate-related crop losses. National data suggests that small-scale producers, or SSPs, are exposed to increasingly variable and extreme climate stresses. In the case of Nigeria, for example, the total number of people from rural agricultural households that reported crop losses to climate is trending up in recent years. At the same time, production and market volatility are outpacing the uptake of technologies and adaptive practices, as adaptation appears to have stagnated. For example, in Ethiopia, the percentage of rural households reporting using improved seeds has doubled between 2010 and 2018, but remains lower than 40%. The use of inorganic fertilizer has stagnated at around 62%. Female-headed households are less likely than male-headed households to use productivity-enhancing inputs. And while climate stresses grow and repeat, options for responding appear to be shrinking. According to LSMSISA household surveys from Ethiopia and Nigeria, doing nothing has become the overwhelmingly most common strategy, as shown by the two tables in this slide. And these strategies are followed by selling assets and reducing consumption, which has long-term consequences for productivity, financial security, and human health. To examine the drivers of discrepancies between self-reported climate shocks and the measured record, we draw from contributions from economics, psychology, and social psychology. The literature shows that adoption of adaptive practices are affected by risk perceptions, and in turn, risk perceptions are influenced by statistical and qualitative characteristics of risks as well as individual risk orientation. Perceived risk depends on a suite of qualitative dimensions affecting exposure and vulnerability. These dimensions include reversibility, proximity and fairness, familiarity, dread control, and experienced events. Research also shows that discrepancies between self-reported climate events and measured shocks could affect adaptation. For example, a 2022 paper by Mayorga and co-authors shows that household head age household size, and access to extension services are associated with adaptation practices. In our empirical implementation, we studied two main hypotheses. First, we test if there's spatial or temporal mismatch of meteorological data to household experience. For spatial mismatch, we test within versus across enumeration area variation in the likelihood of mismatch data. In our data, an enumeration area roughly overlaps with a village. For temporal mismatch, we test the association of proximity of event to survey date and likelihood of mismatch. Research by Cassie and co-authors finds that farmers generalize based on memories of recent events. Our second hypothesis is whether hazard or household characteristics affect recall and risk perceptions. To test this, we look at the severity of hazards and household variability and vulnerability, exposure, and bias, as farmers may use heuristics in interpreting climate and weather events. We focus on reporting highlights from 9 specifications with wave, interview month, and enumeration area fixed effects. Our main data sources are household surveys and remote sensing climate data. We get self-reported shocks data from the LSMS-ISA, with 3 rounds for Ethiopia and 4 rounds for Malawi, with the earliest from 2010 and the most recent from 2018. We construct indicators for measured shocks using the Center for Climatic Hazards, CHIRP's daily rainfall measurements at a resolution of 0.05 degrees. We calculate total rainfall, maximum 5-day rainfall, and maximum consecutive dry days during the growing season and create z-scores with respect to mean and standard deviation in the previous 20 years. Finally, we match precipitation variables with LSMS-ISA household data based on enumeration area coordinates. Here we show some figures to confirm that there is mismatch between self-reported and measured shocks. In the figures in the x-axis, we have z-scores of weather variables, which capture deviations from a long-term normal trend, rather than abnormal values above or below some normative thresholds. The graph on the left shows a weak association between the z-score of maximum 5-day rainfall and the likelihood of self-reporting flooding for z-scores of maximum 5-day rainfall greater than -1. For Ethiopia, in the graph that is in the middle, we see that about half of households exposed to total rainfall z-scores of less than -1 report exposure to drought. That is, low rainfall seems to be associated with the probability of self-reporting drought in Ethiopia. While there is mismatch between self-reported and measured shocks, there seems to be a positive relationship between exposure to and self-report of shocks. In general, there seems to be greater agreement for drought than for flooding measures. Flooding is more complex because it can be caused not only by high rainfall concentrated in a short period of time, but also from overflowing of nearby rivers. So, we defined measured exposure to flooding as a z-score more than 1 for maximum 5-day rainfall. Similarly, we defined measured exposure to drought as a z-score of total rainfall less than -1 or a maximum dry days z-score of more than 1. A false positive is when a household is not exposed to a measured shock, but self-reports that shock. While a false negative is when a household exposed to a shock does not report that shock in the household survey data. In this slide, we show crossed-up tables of exposure to shock and self-reported flooding or drought, and simple chi-square tests show that the likelihood of reporting a false positive conditional on exposure and a false negative conditional on exposure to shocks are statistically different. The results apply for maximum 5-day rainfall and flooding in Malawi, as well as total rainfall and drought, and consecutive dry days and drought in Ethiopia. Our household survey data samples contain several households per enumeration area, where, as we said, an enumeration area roughly corresponds with a village. We run ANOVA tests on whether mismatches vary across enumeration areas and survey waves. And we consistently find that mismatches are unevenly distributed across CAs and survey waves, and that therefore matches are not randomly distributed. So we're interested in analyzing how household and hazard factors might influence recall and perceptions. The idea is to run a regression where the dependent variable is a DOM equal to 1 if there is a mismatch. But we also run analysis restricting the sample. When the sample is restricted to exposure, the outcome is a dummy equal to 1 if a false negative of exposure is reported and 0 otherwise. Similarly, when the sample is restricted to households that were not exposed to a shock in the measured data, the outcome is a dummy variable equal to 1 if a false positive is self-reported in household data and 0 otherwise. The effect of risk attitudes and preferences is not testable with LSMS ISA data, but we test for vulnerability, past exposure, and access to climate information by controlling for household total assets in the form of land and livestock holdings, timing of the shock, and other variables. We focus on reporting results for maximum 5-day rainfall and flooding in Malawi, as well as total rainfall and drought, and consecutive dry days and drought in Ethiopia. So here are our preliminary findings for Malawi and flooding. In columns 1 and 2, we see that land cultivated is associated with a higher chance of mismatch, or, as in the case of column 2, of reporting a false positive, suggesting that increased resilience for households with larger asset holdings. However, as shown in column 3, total livestock holdings increase the probability to report mismatches in general and false positives in particular. We also see that households in Malawi exports to maximum 5-day rainfall with z-score greater than 1 are more likely to report false negatives of flooding if exposed to measured shocks in consecutive years, as shown by the T-1 maximum 5-day rainfall greater than 1 standard deviation dummy. Now we look at the regression results for total rainfall and drought in Ethiopia, where exposure to shock is defined as having a z-score less than 1 of total rainfall. Column 3 indicates that households reporting a higher number of self-reported shocks, excluding drought, are more likely to report false positives, suggesting that families affected by non-weather shocks or other covariate shocks are more likely to self-report exposure to drought shocks. For the case of consecutive dry days and drought in Ethiopia, the results show that households exposed to more shocks in recent years, to more shocks in the same period, are less likely to report false negatives. These are some of our main estimation results so far. So to conclude the presentation, we present preliminary takeaways and direction for future work. Our models showed indications that assets, such as livestock, may influence mismatches between observed and reported shocks. And in particular, households that report many shocks tend to match at higher rates according to our initial regressions. Remotely sensed precipitation measures had higher levels of agreement for drought than for flooding, as flooding tends to be more complex. For example, a year with high rainfall may not have any flood events. We intend to use other remote sensing sources such as MODIS that may provide better indications of experienced flooding. We also think that models may benefit from accounting for nonlinear interactions between event severity and reporting likelihood. So this has been the presentation for this project. Thank you for your time, and I look forward to the 2024 Data for Policy conference.